Okay, we'll continue with the measurement and management. In the first part of the video, you saw the market risk concept, right? Why it is important, and uh, it has been, carefully supervised by the regulators, right? The central bank, and also Financial Services Authority. And we know that in every country, uh, the power sharing of regulators might be different, right? In many Commonwealth countries, we have the central bank playing a role as like monetary authority only. You see in Singapore, we have MAS, Monetary Authority of Singapore, and in another country like the United States, they have different configuration. We talked about this in the earlier part of the course. But now we'll see the measurement and management. We'll see more technical stuff now. Okay, so we have several methods, uh, like renowned approaches to measuring and of course managing the market risk, right? So this is, I think, one of the most famous one, the JPM risk matrix. You know the terminology that VaR, value at risk, very famous, has been used for so many decades. And then the more historic type of method, is back simulation or historic simulation, and then Monte Carlo simulation. This is a modern, also modern type, and we'll see later in using Monte Carlo simulation. Actually, we try to uh, solve the problem of the lacking of data, the situation of which developing countries are usually facing. Right? So in more developed countries, they have like long series of data. Right? So time series data wouldn't be a problem, right? Because they already have like a long series or collection of data. But in many developing countries, where like the previous 1 or 2 decades, they didn't really estimated things, they didn't really hold the records well, then data would be quite lacking in making a conclusion about or a proper estimate about value at risk, for example. So Monte Carlo simulation could help a lot because we could replicate, we could iterate the data collection process using the same distribution. Same distribution means the same mean and variance, but we have a lot of data, simulated data. We call it a bootstrapping method. So expected shortfall, this is newer. This could be used in combination with the value at risk. Okay, so we'll see each one right now. So we'll start with value at risk. The value at risk, right? You see the name, value at risk. So this is the value that's in the borderline. That's why we call it that value at risk. But we have another term here, DEAR, right? Daily earnings at risk. So this is daily VaR, daily VaR. So just what's that? The definition of uh, the daily VaR is called DEAR, right? So daily earnings at risk. But the common term is value at risk, right? VaR, value at risk. So you see the terminology, right? Value at risk. So if I draw confidence interval, I think you're quite familiar with this one. You have your expected value here. You have your expected value, and then you have your sigma, your standard deviation. Right? So your standard deviation would determine the deviation, right? The deviation. So let's say here I have 1 point here, and I have 1 point here, and you have a confidence interval. Right? Confidence interval, you could use at 90%, you could 95, or maybe 99 to be more certain. At 99%, it means that here is 0.5, right? And this would be 0.5, right, percent. Right? So if I change the case, if the confidence interval is 95, then In the left, it would be 2.5%. In the right, at the right hand side would be 2.5%, right? So you can imagine. So if I use 98%, this would be 1 and 1, right? Okay, so you see, let's imagine here this one, right? This point. You wouldn't care too much about this point, right? Because you see, if we have a certain value here, let's say $1 million here, right? 1 million or whatever, 10 million or anything. So what is the meaning of this point? Right? This point means that the possibility of getting more than 1 million is 1%. And you see the logic, right? Even with picture, you can suggest a proposition or an idea here, right? So the possibility of having more than 1 million is 1%. So you wouldn't care about this, right? Because this is good news, right? In terms of risk management, you don't really care about the right side because it is good news. If it happens, yeah, you don't have anything to worry about. But what you care about, what you are concerned about is this one, right? This is called value at risk, right? Value at risk, because this is the value at risk. Let's say this is what, minus 2 million maybe. We'll calculate in a little while, but just mention any number here. Minus 2 million. So the possibility of losing more than 2 million is 1%. That's why we call it value at risk 1%, right? So this is very easy statistical concept, right? That's why we call it value at risk. So the value at risk of 1% here is 2 million, meaning that the possibility of losing more than 2 million, the possibility of losing more than 2 million is 1%. Okay, so let's see some examples here. We'll apply this concept to many types of securities, from the fixed income and then the currency or foreign exchange, and also to equity. So we'll start from the basic concept here. So DEAR, this is again value at risk of 1 day. That's why we call it daily earnings at risk, right? So the basic concept is always the same for any type of instrument. That is what dollar market of. So you can simply call it what value of your position. So your exposure, right? The value of your exposure multiplied by the price volatility. Here's the thing, right? Price volatility would be different. Would be differently measured from one instrument to another. That's the main difference. But the basic principle remains the same, right? So the value of your exposure multiplied by the price volatility. Okay, so let's start with the fixed income, right? First type of instrument, the fixed income. So you see here, this is the market value of position, right? Your exposure, and this would be your. Now the second part of the equation would be your volatility. So for the fixed income securities, we could define the volatility with modified duration multiplied by the potential adverse move in yield. Okay, so let me rewrite it here. So for the fixed income, security, so this is the same, right? So value at risk is always the amount of your exposure or the market value of your position, right? Multiplied by volatility. Now, how to define volatility for fixed income? This would be your modified duration multiplied by potential adverse move. Adverse means a bad thing, right? Adverse, like extreme or negative thing. So here, right, the volatility is defined as this, right? Okay, so let's see an example. So we see an example here. What is the information here? So you might need like 30 seconds to 1 minute to read this. So this is the important information, see? During the last year, so you believe that 1 year data is enough, 1 year data are enough, but you could use, of course, more than one. You could use like 10 years or 20 years, but this is always the dilemma in statistics that we are going to see in the historic method, right? So if you have long time series of data, then of course, statistically, it will be more robust, right? More robust, healthier, right? In terms of the statistical robustness, right, of the measurement. But on the other hand, the long time series of data, long series of data could be questionable, right, as to whether they come from the same distribution. We'll talk about this a bit later. But see here, suppose that during last year, so we believe that last year data or 1 year data are sufficient to make the inferences about the information here. The mean change in daily yields on 7-year zero coupon bonds was 0%, but the standard deviation was 10 basis points, right? So you see, the data show us that last year the change in yield, right, or market rate, market interest rate. So the change in market interest rate last year was on average 0, right? The mean was 0, but what's that? The move, right? The standard deviation, the volatility was 10 basis points, right? So I hope you're familiar with the terminology basis points. Basis points means what? Divided by 10,000, right? Okay, divided by 10,000. So this is 1 basis point, right? So 1 basis point. So there are 4 decimals, right? So if I say, very simple, right? If I say 5 basis points, so you could write it this way, right? 5 basis points, right? What about 15 basis points? 15 basis points, very easy, right? So what about 100 basis points? 100 basis points means 1%. You can write it this way, right? Full decimals, and you can say whatever basis points you want. 250 basis points, okay, and so forth. So very easy. So 1 over 10,000 is called basis points. So in this example, what is it? 10 basis points. So you see that based on the information from last year data, the mean is 0, and the standard deviation was 10 basis points. Okay. Okay, so here and here, 2 important information, right? And what is the modified duration? We can find out here. 0 coupon bond, 7-year, right? Remember from our discussion on interest rate risk, this is a special case, right? 0 coupon bond, 0 coupon security is a special case where its maturity will be exactly the same as its duration, right? So we immediately know that the duration of the bond would be 7 years, right? Would be 7 years as well, because the maturity is 7 years. Okay, so let's put this into the analysis. Okay, see from our definition here, we know the exposure, right? The exposure in the story is, how much is it? No information here, maybe here. Oh, we know from here, right? 1 million. Okay, so the exposure is 1 million, right? The exposure is 1 million, and then the volatility. Now we have to calculate the volatility of. So the volatility is defined as or could be measured as modified duration multiplied by potential adverse move, right? So what is the modified duration again? Modified duration would be, hope you still remember, right? Modified duration is the duration divided by 1 plus the original interest rate, right? So in our story here, the duration is 7 years because this is a zero coupon bond with a 7-year maturity. So again, for the special case, such as a zero coupon bond, the maturity is always the same as its duration, right? So 1 plus, what's the original interest rate? No information here, maybe this one. Oh, we don't have the information on the original interest rate. Okay, no information is given here, but they gave us what, the modified duration here. So it's 7 divided by 1 plus something, right? Maybe, what is that, 8% or something? And you got 6.527. So again, the example is lousy. So it tells you immediately the modified duration, but you know the process, right? Modified duration is the duration divided by 1 plus original interest rate. So yeah, maybe 8% or 7% or something like that. But we got the modified duration already. They told us, right? The information already tells us that the modified duration is 6.527. Okay, so the modified duration is 6.527. This is told by the information, but again, you can calculate using the duration divided by 1 plus original interest rate. So again, the volatility is modified duration multiplied by the adverse move, right? Potential adverse move. So you know the modified duration as given, right, in the example. Now, what is the adverse move again? You see the very important information. Right, the mean was 0, right? Last year, mean change in the market interest rate on 7-year zero coupon bond was 0%. So the mean was 0%, but the standard deviation was 10 basis points. So this is the problem here, right? So the potential adverse move is 10 basis points, right? So 10 basis points, something like that, right? However, I think you would be familiar with this in your statistics. You know that when you try to estimate your confidence interval, so this is a statistical thing, right? You have the what we call it, the type 1 error, right? Type 1 error means there's a possibility that you reject the hypothesis that should not be rejected, right? So we call it alpha, right? We call it alpha there. So type 1 error. So nothing is perfect, right? So you have the room for error there. But you have to admit. So for example here, if this is 95, this would be 2.5, right? And 2.5. So there we are saying that if the confidence interval is 95%, then what you are saying here, what you are concluding, what you are saying is correct 95% of the time. See the thing, right? So there's a possibility that there's a possibility of 5% that what you are saying may not be correct, right? So what you are saying, what you are concluding is 95% correct of the time, 95% of the time correct, right? Okay, so and similarly, if this is not 95, but maybe 98, okay, 98, right? So this would be 1, right? This would be 1. So we have a margin of error, right? So to the left and to the right. That's why you need the coefficient on the sigma, right? Coefficient on the sigma, right? What is the coefficient there? The the CDF, right? The cumulative density function value of your sigma. Your sigma is your standard deviation. So we have sigma here. We already have the sigma, but we need the coefficient, right? To to admit the fact that in statistical things, nothing is perfect. You have the room for error. So now, what is the coefficient here? It depends on the distribution we are using. And of course, as for the sake of brevity, for the sake of the example, we will use the simplest distribution, which is what? Normal distribution, or Z, right? Z distribution is the normal distribution. Okay, so this is the thing that I want to remind you. Okay, so you don't need to memorize any coefficient. Okay, you don't need to memorize because this is not appropriate, right? And nor should you bring statistical tables everywhere, because this is not the time of whatever from the past, right? The 1930s or something, right? Or Majapahit time or something, right? So you're not supposed to bring statistical tables everywhere because you have Excel, right? You have Excel, you have your Apple, you have your Android, and something like that. So, and you're not supposed to memorize this. However, if you work in this area, I mean, if you are like a business modeler or a risk manager or maybe a business failure or something like that, you might memorize this accidentally. Right? So by accident, you memorize this because you use them a lot. For example, by accident, I would remember this, right? So if the coefficient is 165, I mean again the value of in the CDF table for Z distribution, for normal distribution. So I would know that the confidence interval would be what, 90%? You see, I memorized by accident, just not because I intentionally memorized, because we use it a lot, right? In my daily works, in my daily business. 196, this is the famous one, right? Would be 95% confidence interval. So you might memorize by accident, right? Because you use it quite almost every day. Maybe 233 would be 98. 258 with 99. Okay, so now we are going to choose, right? Which value at risk you want to measure. So if you want to measure, maybe example here, if you use 95%, what is the value at risk there? Can you imagine, right? 95 would be what? 95 and then 2.5, right? So what value at risk is it? 2.5, right? 2.5. So if you are using 98%, what value at risk is that? 1, right? Because 1 at the left, 1 at the right. So this is value at risk of 1. Because if you follow the story here, we are only concerned about the this one, right? The negative part, because the right part is good news. Of course, you're not concerned about. If you use 99% or 2.58 as the coefficient, then you're measuring what? Half, right? The VaR of 0.5%. Okay, so now we have to choose based on Basel, the third regulation, we must use at least VaR 1%. VaR of 1% is this one, right? If you want to use VaR of 5%, then which one is that? VaR of 5%, then this one. See, your confidence interval is 90. So at the left, 5, at the right, 5. That's why this is VaR 5%, right? But if you're using VaR of 1%, then this is the coefficient, right? 2.33. Okay, so this has to be multiplied with 2.33, the coefficient, right? To show the distribution, right? The CDF of the distribution. Okay, so then it has been calculated for us here. See, the modified duration is 6.527. Now here is what? Here is the coefficient that we are choosing is 2.33. Why? Because we are doing the VaR of 1%, right? VaR of 1%. So VaR of 1% means a confidence interval of 98%, right? 98% and then 1% at the left, 1 at the right. So this is VaR 1% multiplied by 10 basis points. And we get this, right? Okay, so we find out that the volatility is 1521%. Okay, so let's wrap it up here. So your volatility is 1521%. Right? Where is it from again? Modified duration multiplied by the adverse move. Your adverse move is the what's that coefficient? Normal distribution coefficient multiplied by your sigma or your standard deviation. Okay, and then what is the value at risk or DEAR? DEAR is again daily, right? DEAR 1%. What is your exposure in the story? 1 million. Exposure in the story is 1 million multiplied by your volatility. So you get what? 15,210. Now, what is the meaning? So here 1%, right? And the point here is 15,210. So this could be easily interpreted, right? So the possibility of losing more than 15,210 is 1%, right? That's why this is called what? Value at risk. Or for the daily case, this is called the daily earnings at risk. Okay, so let's try like VaR of 5%. You can calculate quickly. What if we want to know the VaR or DEAR of 5%? So what is changing there? So the DEAR of 5% is, what's that? The exposure. This is 1 million, right? In the story multiplied by volatility. So exposure is 1 million. Right, what is the volatility now? Volatility is your modified duration, right, multiplied by the sigma, and then the coefficient, right? And what is the coefficient for 5%? Coefficient for 5% is this one, right? See, confidence interval of 90%. So at the left 5%, at the right 5%. So for 5% is using this coefficient, right? 165. So is that 1 million? And what is the modified duration again? 6527 in the story here. Modified duration is 6527 years times 165, and the standard deviation according to last year data was 10 basis points, right? 10 basis points. Okay. So how much is it? Let's calculate. Okay, so this is on my calculation. 1 million multiplied by 0.0108. Okay, so how much is it? 10,769 and 55 cents, or 770, right? If you want to round it up. So what is the conclusion here? The VaR or DIR of 5% is 10,769. Right? So what's the meaning there? The possibility of losing more than 10,769 is 5%. Right? And the possibility of losing more than 15,210 is 1%. Right? So if we draw it, would be this, right? So if this is one, maybe here is 15,000 minus 15,000, what is that again? 210. Oh, that picture. So 10,000, and here is minus 15,210. And so see, the possibility of losing more than 15,210 is 1%. But the possibility of losing more than 10,770 is what? 5%, right? Very easy. Easy statistical concept. But the name is good, right? Value at risk. Okay, so this is for fixed income, right? Fixed income, confidence interval. We studied this a lot in statistics, right? Confidence interval. So just remember the use of the coefficient. If you don't remember, just go to Excel, and you can find the coefficient on the sigma, on the CDF. Right? Okay, so if you want to calculate the value at risk for several days, then you have to multiply by the square root of n, not multiplied by n. How it happens? This is out of our scope today. Maybe someday we'll make a video on the econometrics of this, right? So yeah, if standard deviation grows, it doesn't grow by with n, but with the square root of n. Right? So for example, 5 days from our previous calculation, this is what VaR 5%, right? So what's the meaning again? The possibility of losing more than 10,770 is 5%. That's why we call it VaR of 5%. Right? So VaR 5 for 5 days. So if you want to find 10 days, then you multiply by the square root of 10, right? Or 22 days will be the square root of 22 and so forth. So based on the Bessel the third, if you use in the internal model like this, like the VaR method, JP-Emrys matrix, minimum you have to multiply by, I think 10. Yeah, minimum 10 days. Yeah? And you have to multiply by the, what's that, the factor of 3. Minimum 3 and maximum 4, but usually you multiply by 3. We'll see that later in our discussion. Okay, I hope it's quite clear for fixed income. It's quite easy. The use of the confidence interval as a statistical concept. So that's why we call it value at risk. So once again, if we summarize the meaning of the value at risk, is the value at which the possibility of losing more than that value is a certain percent, right? Name value of risk of n%, right? So once again, if the value at risk of 1% is 15,000, for example, then it means the possibility of losing more than 15,000 is 1%. Right? So next one, next instrument is currency risk, foreign exchange. You see, the principle is always the same, right? The basic principle is always the amount of your exposure multiplied by the volatility. But this time, this is like foreign exchange, right? Currency volatility. Let's go straight into the story here. 800,000 exposure, 800,000 euros. Information is it? Oh, this is the exchange rate. 125, right? $125 per euro. Okay, 800,000. So let's suppose that we are an American financial institution. So we want to translate it back into US dollar. Again, because supposedly you're an American financial institution here, and the spot rate is like this, right? So you know that the amount is 800,000 euros, and this is the exchange rate, you see. So the currencies are the same at the back, right? If they're the same at the back, you multiply. You multiply them, right? If they're the same in front, you divide. Right? It's very easy principle. So 800,000 euros. So they are the same at the back. This is what the anchor currency. So they are the same at the back currency. So you multiply 800,000 multiplied by 125, of course, is what? 1 million, right? So this is your position, your exposure. Now, what is your volatility? So it's useful, right? The VaR is always your exposure multiplied by volatility. So you know your exposure here, 1 million. And what is the story now? See, oh, no, sorry. Oh, not yet. Maybe here. Okay, here. So over the past year, again, you believe that 1 year data are sufficient to make an inference about the mean and variance, right, or mean and standard deviation. So you find that the volatility of standard deviation, you see, the volatility or standard deviation of daily percentage changes in the spot exchange rate was 56.5 basis points. So 56.5, can you imagine? 56.5, right? 56, right? 0.5. Okay. So this is the information about the previous year's standard deviation that we use as a proxy. So again, right, to determine the standard deviation, you have to what's that, make a representation, right, or a proxy, and you believe that maybe the past year data are sufficient or are appropriate to make the inference. Okay, so now going back to here, we know that the volatility here is what's that again? 56.5, right? So 56 basis point 0.5, right? This is your standard deviation based on last year's data. The standard deviation of the change or the changes in spot exchange rate between US dollar and euro, right? But again, here you need this is the sigma, right? And you need the coefficient, right? The coefficient. So now you have to decide again, what value at risk do you want? What value at risk you want in this case? If you want value at risk VaR 1, right? Value at risk of 1%, then this would be the coefficient, right? 2.33. Because once again, 2.33 is the coefficient for a confidence interval of 98%. So with a confidence interval of 98%, you have 1% at the left and 1% at the right. So that's why this is the VaR 1, VaR of 1%. So you should use what, 2.33. This is multiplied with 2.33. And we get what? Has been calculated, I think. Yes, so 56.5 basis points multiplied by its coefficient. So we choose 2.33 because we want to estimate the VaR of 1%. So if you want the VaR of 5%, then the coefficient should be 165, right? If you want the VaR of 0.5%, then the coefficient should be 2.58, and so forth, right? So we are using VaR of 1%, then the volatility is this one, 131 basis points, somethings. And then what is VaR again? VaR is exposure multiplied by volatility. Ooh. So we get 13,164. Right? Once again, this is the exposure, 1 million, multiplied by volatility. So volatility is the standard deviation from the past multiplied by its coefficient, right? So 13,164. What's the meaning here? The possibility of losing more than 13,164 is 1%. Again, because we are using 233, right? So what if we use the VaR of 5%? Then this should be 65. So let me calculate 6. So 1.65 multiplied by 65.5 basis points, right? So you get here 0.0093. So 93 basis points if you use 165 for the VaR 5%, right? And if you multiply by 1 million, our exposure, so you get 9,322 and 50 cents. So we are this is the VaR 5, right? VaR of 5%. So the possibility of losing more than 9,322 is 5%. But the probability of losing more than 13,164 is 1%. Okay, very easy. The principle is always the same. Exposure multiplied by volatility. Okay, so the third type is equity. The first type was fixed income. Second type was foreign exchange or currency, and now the third type, this is equity. So equity, then we have a lot of choices, right, to determine the risk, right? Risk and return. So in this context, we are concerned about the risk, and we can use the Markovitz method. You can use William Sharp's CAPM, and I think we use the latter, not the former. We use the latter, the CAPM by William Sharp. So as told by William Sharp, the total risk, right? So total variance of anything, right? An instrument. Right? This has two components, right? I have the systematic component and, of course, the unsystematic component. For the systematic components, we have what? We have the beta of the asset, right? Multiplied by the variance of the market So the variance of the market return. Okay, this is called what? The systematic component, right? Systematic. And then, of course, we have the unsystematic one. Unsystematic one would be the variance of the error, right, of the regression. So if you're doing regression, this could easily be found, right, in your regression outputs. It's something that you don't do by hands, right? But you have to know, of course, you have to know the mathematical logics, but you don't do it by hands, right? So if you do it by hands, then maybe cats will laugh at you, right? Because even cats are using calculator. But you have to know the mathematical logic. Right? So now we go back to the story to see what our inputs are, unsystematic. Right? So 1 million trading position. This is a lazy example. They always use 1 million to make it easy to calculate. Let's assume that. Can you imagine if they use like whatever 752,185 or something? Then it takes a bit more effort to calculate. Right? But 1 million is always an easy amount to use. Easy example. Beta is 1. Beta is 1. Right? So you multiply anything by 1, it would be 1. Right? So let's see the story here. Over the last year, you see the information there. Market return, right? The standard deviation of the market return was 200 basis points, right? 200, I remember 200 would be what? This. 200 basis points. Okay, so that's the information, right? So see, the principle is always the same. VaR is always what? Exposure multiplied by volatility. But the volatility now is this, right? We have two components now. The exposure is, of course, 1 million, as always. So now we have to define the volatility. In the story, we know that, again, we have two components there. The sigma, or maybe more appropriate, sigma, right? The sigma multiplied by its coefficient, of course. Now let's calculate the. So we set apart the coefficient. I will come back to it later. But what is this one? So again, the variance, we wrote it before, but we repeat it here. That's the variance of the error. Okay, so what's the beta in our story? We can, to make it easy, we take the square root of everything. See, square root of this, square root of this, square root of this, square root of this. So square root of everything. So we get this, right? We get the standard deviation instead of variance. So what is the beta in the story? Lazy story, 1, right? 1. And then what is the volatility? 200 basis points here. Right? This is the standard deviation of the market return. So multiplied by 200 basis points. I hope you remember the concept of the portfolio theory, okay? So if this asset is part of a well-diversified portfolio, then the unsystematic risk would diminish quickly and finally eliminated. Or could be diversified away perfectly, the unsystematic part, okay? If you don't remember, just watch my videos on portfolio theory. There are several parts there. But once again, if this asset is part of a well-diversified portfolio, then you could safely assume that the unsystematic risk would be very low or even eliminated, right? So this could be 0. You see, lazy example, right? So you have 1 multiplied by this, of course, it will remain 200 basis points. Okay, so now 1 million multiplied by, now the sigma is 1 multiplied by this plus 0, of course, is 200 basis points. Now, what is the coefficient? What is the coefficient? Okay, so we have to choose again. What VaR do you want? Or what VaR you want to choose here? Okay, so if you want the VaR of 5%, then you choose 165, right? Because the confidence interval is 90%. But if you want to choose, you want to measure the VaR of 1%, then the coefficient should be 2.33. So we'll choose 1%. Okay, so the coefficient would be 2.33. And we'll get, it has been calculated. Okay, so yeah, 46,600. Okay, 46,600. What's the meaning again? VaR of 1% is 46,600. So the possibility of losing more than 46,600 is 1%, right? So the possibility of losing more than 46,600 is 1%. Okay, so it's very easy. Now we'll combine, let's assume that we combine the 3 types of instruments as a portfolio. So we'll apply again the Markovitz full method of estimating the portfolio risk, right? So see here, the deal of the first, right, square, and so forth, right? We have seen this in the also the portfolio context for market risk, and also in portfolio theory discussions, right? So we apply the Markovitz method. So what's the idea here is that we couldn't just, add all of them together, because we'll get the portfolio benefit, right? So we have, in this example, we have fixed income security, we have the foreign exchange, and we also have equity, right? So we have at least 3 instruments, right, in this example. So in estimating the total value at risk, right, total market risk, we cannot simply just add them together, because that way we are ignoring the portfolio benefit, or the benefit from diversification. So we have to combine them in a portfolio fashion, like what we did also with the with the credit risk, right? The portfolio context for credit risk that we did before. So this is a similar thing. So if you let's compare the results, right? So what was the this one, right? The value at risk of 1% for fixed income, 15,210. If I add this with the foreign exchange, market risk of VaR of 1% is 13,164. Okay? If I add them to this one, uh, 46,600. Okay, so the total value at risk of 1% for the 3 combined instruments would be 74,974. Okay, and you see the results. So the real one is 56,443 instead of 74,974. So if we just simply add 3 of them together, right? The value of risk of 1% for fixed income, and that for foreign exchange, and that for equity, we'll get 74,974. But you see the real one, based on the Markovitz method that we apply here, and we actually get the combined value at risk or the portfolio value at risk of 56,443. So the difference is called what? The benefit from diversification, right? The benefit from portfolio. Okay, so the real one is 56,443 using the Markovitz method, right? The portfolio risk measure or estimation by Harry Markovitz. But if you simply add them together, you get 74,000. So the difference is called the benefit from portfolio or diversification. So we need the correlations. You remember, right? Correlations. We need correlations between assets, and here we have 3 assets, right? So we need the pairs, right, between fixed income and foreign exchange, fixed income and equity, and then equity and foreign exchange. This is example, right? Example of a financial institution, the interest rate risk here, right? The interest rate risk, interest bear is 48, right? We saw it before, right? The daily earnings at risk measurement. Then foreign exchange risk. Okay. And see, these are examples of the big banks in the United States. It's quite like 65 million. And Citigroup has an average year, again, daily earnings at risk is far for one day, right? 109 million, right? That's really big, right? So what's the interpretation again? The possibility of losing more than 109 million for the Citigroup, right? The possibility of losing more than 109 million is 1%. And even maximum, you see, during the year, it reached 159 million, right? That's quite scary, right? Because that's failure at risk for one day. The possibility of losing more than 159 million is 1%. So it might sound quite low, right? 1%, but if you're talking about a big amount of money, 1% is very dangerous, right? Very dangerous. 1% means what? Out of the 100 iterations, right? 100 possible events, one of them falls into the category, right? That's quite big, right? It's quite big. Of course, if you're talking about something not that material, right? Not that substantial, you might not feel that bad, right? For example, the possibility of getting a C, right, in your grade is 1%, right? Possibility of getting worse than B is 1%. Though you're thinking, oh, it's small, right? Small, because nothing is involved here. But if you're talking about hundreds of millions, then this is a big problem, right? 1% is dangerous. Or if you see the statistics for the fatality rate for the recent virus, right? Even 5% is bad, right? Because we are talking about what, 3 million people, right? 3 million people, and 5% of it would be like what, 150 or something, right? It sounds small, but actually it's really bad, right? 5% is already bad. Even 1% is bad enough, right? If you think about it, 3 million people, 1% would be like what, 3,000 or 30,000 even. Yeah, 30,000. 1% would be 30,000. That's terrible, right? And the same could be thought about for financial institutions. Okay, so we'll continue with the second method, right? We saw the JPM risk matrix, or the famous name, failure at risk. Now the second one, the historic approach. This is a lazy method. We're not saying that lazy method is always bad, right? But this is just easier, could save a lot of money, right? Because you're using your own historical data. So you could save a lot of money, you could save a lot of time, right, energy and effort. Not necessarily worse in terms of interpretation or conclusion, but most of the time this method is facing with a dilemma, right? Statistical dilemma. So I told you before, right? If you want to use the historic approach, we have a dilemma. If we have a short series of data, right? The data are too short. Maybe you only have proper data for 3 years, right? Definitely they are not sufficient. They are not robust to make any statistical inferences, right? So too short, right? Too short. So data are not robust. So statistical conclusion might not be robust as well. They're not robust either, right? However, if you have like long series of data, don't think that that's always a good thing, right? Not necessarily good, because think about it, right? If you have long series of data, then of course statistically the analysis would be more sound, right? Or more robust, right? But what is the weakness there? The data might come from these different distributions. Then you're measuring different things, right? You're measuring different things. So this would be tied with like characteristics of countries, right? Every country will have like different data characteristics. For example, if you talk about the United States, if you get the data from 1980s or even 70s, you could safely say that their distributions might be more or less the same, because the United States as an established country has been has been having this kind of similar market characteristics, right? Similar development from maybe the last 2 or 3 decades, right? So situations are quite similar. Of course, we are not saying that it's the same, but similar, right? Similar pattern, similar style of making decision, similar style of regulations, and so forth. Right? So it's more fortunate, right? Some countries, also in Western Europe, like in Germany, they could safely use longer series of data because their distributions are quite uniform. Not exactly the same, but at least similar or uniform. But if you take developing countries, maybe China or Indonesia, if you think about it, right? This is 2020. Can you imagine the situation in 1980, or not even 1980, maybe 1990s, right? Were things the same or totally different from the current situation? Of course, it's totally different, right? Totally different. 1970s, couldn't imagine even further, right? 1960s, oh, that's like what's that? The uh, new order regime, right? The toppling of the Communist Party movement, right? The Communist Party rebellion or something like that. So it's totally different thing, right? So if we use data from 1970s, right, for such a country, then definitely the distributions are totally different, and your data are useless, right? Your data are super inaccurate, and any statistical inferences that you could come up with would be super biased. It's unusable. So again, this is a dilemma, right? Dilemma. If you have long series of data, you might be happy in terms of the data. The possible robustness of the statistical running, but you have to check whether the data distribution is uniform or the same throughout your analysis period. Otherwise, the data cannot be used. Right? Okay, so historical approach is very easy. So we'll go straight to maybe the example here. Okay, go straight to the example. Let's say you have two currencies, right? Two currencies, yen and Swiss franc. Right? We start with yen. So your what's that? Your closing position. So you have an exposure in Japanese yen of 500 million yens. 500 million yens, and the spot rate right now is 100 per yen. Do it here. So your exposure is 500 million yens. Spot rate is, what's that, 100? 100 per dollar, 100 yens per dollar. Okay, simple question. What are you afraid of? If you have an exposure in yen, what are you afraid of? Of course, the decreasing value of yen, right? So you are afraid of depreciating yen, right? If yen appreciates, you will be happy, right? Because you're holding yens, right? 500 million yens, then you will be unhappy, or you are afraid of depreciating yen if yen value decreases, right? So you start making scenarios, right? Maybe you start with the first scenario. What is the first scenario? Yeah, maybe you make, this is your first scenario, okay? What if yen depreciates to 101? This is the depreciation of yen, right? From 100 to 101. Think about it, right? If today you can buy dollar by paying 100 yens, right? You are afraid that tomorrow to get $1, you have to pay 101 yens. Right? This shows what? What does it show? It shows a depreciation of yen, right? The decreasing value of yen from 100 to 101. Again, once again, right? Today, you can buy $1 by paying 100. Maybe the next day, you have to buy $1 by paying 101. So Japanese yen depreciates. So this is the scenario, the first scenario that you're going to make, right? What if yen depreciates to 101? Then what would be the value of the 500 million? Right now, it would be what? 500 million yens. And then this is the spot rate right now. See, they're the same in front. They're the same in the reference currency. So you divide, right? They're the same in front, you divide. So 500 million divided by 100 is 50,000. What about this? What would the value be of the 500 yens if the spot rate changes to 101 yens per dollar? So 500 million divided by 101. So oops, wait, this is, yeah, okay. So what is that again? 49? Yeah, 49,000, 49,505 or something like that. I think that's been calculated here. Yeah, oh sorry, yeah, I mean 4.9 million. So from 5 million, oh, let me calculate properly, right? 500 million divided by 100 is what? 5 million? 5 million to 4 million 950,495. So what is the difference? So if Japanese yen depreciates by 1 yen per dollar, right, from 100 to 101, then we will lose 49,505. Okay, so this is, what's it, the loss that we will suffer, right? So you see here 500 million. So based on the spot rate, the money right now is $5 million, right? 500 million yens. can be translated into $5 million at the 500 yens per dollar spot rate. But again, if yen depreciates by 1% from 100 to 101 yens per dollar, then our money would be 4.9 million. So we are losing what, 49,000 per 1% depreciation in Japanese yen. And then we do it for the previous day, right? The November 30th, yen depreciates by 0.5%. Then you're losing 24,000. You got the idea, right? If yen depreciates by 1%, you're losing 49,505. If yen depreciates by 0.5%, then how much is it? Of course, half of it, right? You're losing 24,000 something. Okay, and we do it for the days back, right? November 30th, November 29th, November 28th, and so forth. And yeah, until the last, depending on how many days you want to go back, right? Go backward. Okay, then we rank them. We rank them from the worst, right? The worst day to the best. Oh, so we decide to get 500, right? 500 days, right? 500 working days, right? From whatever the dates were. But now you make an order. You rank them from the worst day to the best. Okay, so after ranking, then you decide the position, right? You decide the position. Like if you want the VaR of 5%, VaR of 5%. So out of 500 days, which position is it? 5% of 200. 5% of 500 is 25, right? So this is your VaR of 5%. So 60,756. So what is the conclusion here? According to the historic method, the possibility of losing more than 60,756 is 5%. What about VaR 1? The VaR of 1%. So you have 500 data. 1% means the fifth position, right? The fifth position. So 1% of 500 days, right? 500 data. So the fifth position. So 97,210. So what is the conclusion here? The possibility of losing more than 97,210 is 1%. Okay, so what about Swiss franc? Swiss franc, we are having what? 200, wait, what was that? 20 million, 20 million Swiss franc. So our exposure is 20 million Swiss franc, and the spot rate is what? 110, right? 110 per dollar, right? 110 per dollar. So how much is it? 20 million Swiss franc with spot rate of 110 per dollar, 110 Swiss francs per dollar. You divide, right? They're the same in front. You see the currencies are the same in front. So 20 million divided by 110. So this is our money right now, 18,181,818. Okay, so we make a simulation. See here. Yeah. What if? So what are we afraid of again? You have a long position in Swiss franc, right? You have a long position in Swiss franc, and of course, you are afraid that Swiss franc will depreciate, right? Will decrease in value because you're holding it. You're holding a Swiss franc, and you will not be happy if Swiss franc depreciates. So we make a scenario. What if Swiss franc depreciates by 1%? Depreciates by 1%. So 110 to 10%. Sorry, 1% depreciation. Is 111. Okay, so you start your simulation by making the first iteration or simulation, right? So if the spot rate right now is 110 Swiss francs per dollar, what if the Swiss franc depreciates by 1% to SF 111 Swiss francs per dollar, right? So today you could buy $1 by paying 110 Swiss francs. Maybe tomorrow you have to buy $1 by paying 111 Swiss francs. Okay, and what will happen to our money? 20 million will be worth how much now? 111, 18 million 001, 800. So you're losing some money, right? See, from 18 million 181,000 something to 18 million and 1,800. So you're losing money if Swiss franc depreciates here, right? So for every 1% depreciation of Swiss franc, you will lose $180,000 and $180,018. Okay, for every 1% depreciation. Then you start making the simulation, right? November 30th, Swiss franc depreciates by 0.2. So 1% depreciation will lead to a loss of 180,000 something, right? What about 0.2%? So 0.2% is 1/5, right? Or 20% of 1%, right? So the loss would be 20% of minus 80. So it would be minus 36, whatever it is. Was it 6, 2 or something? Yeah. So 1% depreciation will lead to the loss of 180,000. So the depreciation of 2% of Swiss franc, of course, will lead to 20% of 180,000 loss. Right? And then you continue with previous days for the previous 500 days, and then similarly you make a rank, right? You make a rank from the worst day to the best day, and then you point one position, right? Again, because you have 500 days, the VaR of 5% will be at the, which position is that? 5 of 500, 25th position, right? 25th position. But for the VaR 1%, VaR of 1%, the position would be the 5th position, right? 1% of 500. So you see, 500 data are not many, right? This is not robust at all in statistics. 500 days mean 2 years, right? For the working days, right? It's about 2 years. So this is definitely not robust in statistics. But 500 days are good in terms of distribution because you can be almost perfectly sure that the data from the last 2 years are reminiscent, right? At least reminiscent, but most likely the same in terms of their distributions. Right? So this is a historic method or the lazy method. Lazy doesn't necessarily mean bad, right? Just like students, right? If you have more talent in something, maybe you could be a bit lazier, right? But if you know that you're not talented in that field, then you have to work harder. Right? That's in common sense. Okay, so advantages, simplicity, right? Cheaper, less effort, less energy, less time to do it, right? Doesn't require calculation of the Markovitz portfolio, right? Portfolio method, mean and variance model by Markovitz, or CAPM by William Sharp. doesn't require normal distribution. You don't care even, right? And could show you the worst day, right? In our example, the worst day. But key disadvantages, see, data are too small. 500 observations are nothing, not robust, right? Good distribution uniformity, but yeah, not that robust because the data are not sufficient in numbers. Next one, Monte Carlo simulation. Yeah, this is out of our scope, but this is very useful one. You see, this is actually a continuation of the historical method, right? Historic back simulation. You think about it, from our previous example, we had good data distribution, right? Because we got it from the last 2 years. So definitely they came from the same distribution, right? The 500 data. However, the number of data was not or might not be sufficient, right, to get the statistical robustness. So this could help a lot, right? Monte Carlo simulation. And you can guess, right? Monte Carlo simulation. Where is Monte Carlo? In Monaco, right? Monaco. What place is it famous for? It's casino, right? Casino. So this is interesting, right? So the casino players are, or the casino experts are actually the ones who are highly interested in statistics because they try to beat the house, right? You see, the famous term in the gambling world, we try to make the house broke, right? Break, right? To make them go broke. But I know it's impossible, right? In any kind of statistical analysis, you know that the house is uh, having a higher hand, right? They are at a more favorable position. But against gamblers, always try to find ways to increase the possible winning methods. And how to prove that their methods are working? They must have uh, a lot of data, and of course, you cannot play a lot of data, like 1 million shoes. How can you do 1 million shoes? Right? If I play baccarat, baccarat, the banking and player, and if I have one method, let's say I find a method to consistently beat the house at least maybe 90% of the time, or 80% of the time, or something like that. I need to prove it, right? I need to prove the method in many shoes. So if I tell let's say I tell my fellow player, okay, that who goes to Monte Carlo to go to MBS Singapore, anywhere, I tell them I have a method, and I have proved it in like 100 shoes, and maybe the guy will laugh at me, right? Because 100 shoes are nothing. So they ask me, can you prove it for 1 million shoes? Then of course I cannot play 1 million shoes within a short period of time, right? That would take me years. So that's why there's Monte Carlo simulation, right? So again, the statistical methods are well developed for the casino players because they try to beat the house. Okay, so now I try to make the limited data that I have, maybe 500 days or yeah, anything, right? 100 shoes that I have, right, for the baccarat play, or in the previous example, it was 500 days for the failure at risk calculation. So I want to make sure that I have like enough data, but with the same distribution. So this is the way to do it, like Monte Carlo simulation. So I bootstrap the data. We call it bootstrapping, right? So you bootstrap the data from 500 to 1,000, or maybe even here you see 10,000, 5,000, or whatever. But the data distribution is maintained. Data distribution means the mean and variance, right? So the mean and variance of the data are maintained. But now we have that 10,000 data. How do we do it? It's out of our scope, but I can give a little bit a slight clue of it, right? How to do it. So you can see an example also here, but let me show you. Okay, so you need to make iterations, right? In Monte Carlo, you need to make iteration. How to do the iteration? Actually, it's not that difficult with the advancement of technology. So, for example, iteration number one. Right? Iteration number one, You could put in this now in Excel, but you have to know, of course, you have to know the, what's that, your some information, right? For example, the variance of the data, your previous data, right? What is the variance, and what is your, for example, your interest rate right now, the current interest rate. So the interest rate is usually proxied by risk-free rate. So the iteration will look like this. The E, right? E is the exponent, right? 2 point, you remember from your high school, 2.7183, right? 2.7183, like the E exponent, right? To the power of, not to the power of the interest rate, right? Interest rate, and then minus half your variance, okay? Multiplied by the time. Time, of course, is in year. So if this is 1 day, then this would be what, 1 divided by 250 working days, right, in 1 year, right? So if this is yeah, whatever 20 days, this would be what, 20 divided by 250, right? So T is in year, right? Time in year, and then you plus your standard deviation. Be careful now. This is standard deviation, right? Standard deviation. This is plus, right? Plus standard deviation multiplied by the square root of time, right? Square root of time, and then you multiply by. Now you put into the Excel, right? Say norm as inverse, right? Norm as inverse. You know that in Black and Scholes option pricing model, you have the D1 and D2, and you have to find the CDF of the D1 and D2. You use norm as this, right? Norm.as.this distribution, the DIST. But here, norm as inverse. So you inverse it, right? And then you multiply by random. So you multiply by the random. Remember, right? Random. Okay. Yeah. Okay. So you have the. You can put in Excel or any other software. So you get one iteration, right? You get one iteration. Then you repeat the iteration for using the data table or something. I'm quite familiar with Excel, but I'm not familiar with other software, okay? You can use data table. You can replicate this for whatever, 10,000 times or 5,000, very easy, right? So with the advancement of technology, I think the more important things are how you determine the inputs, okay? But you have Excel, you have everything, you put everything in. Even cats can do it. As long as you know the inputs, right? So iteration, and then you put into data table, you do it for 5,000 or 10,000 times or anything. Okay, so again, what is the idea here? The idea here is that you try to enlarge the data, but the data have the same distribution, so the same mean and variance. So you maintain the the integrity of the data in terms of distribution, but now you not only have 500, but you have 5,000 or 10,000 or something like that. So with the huge series of data, then hopefully your statistical analysis will be more healthy, right? More robust, right? This is again out of our scope. Maybe the next time I will make a special video on Monte Carlo simulation. This is very easy, again, in modern times, right? It's not something that only super experts can do it, but even with Excel, we can do it easily. Okay, so expected shortfall is similar in concept to value at risk, but so expected shortfall has become famous since the 2008 to 2010 financial crisis. So let me draw the idea here. So with the value at risk, here, right? Let's talk about 1%, okay? So 1% value at risk. So obviously this is 98, right? 98. Okay, so this is the value at risk. So again, what is the meaning? For example, this is at 1 million, 15,000, 200,000 or anything. So the possibility of losing more than this amount, maybe whatever, yeah, 20,000, right? The possibility of losing more than 20,000 is 1%, right? You see the picture there. Right? But it turns out that during the financial crisis of 2008 to 2010, we found a lot of mistakes by value at risk because you never know what were behind this, right? So see my statement, right? You think about my statement again. My statement says that the possibility of losing more than 20,000 is 1%. So it looks small, right? So you think about it, the possibility of losing more than 20,000 is only 1%. So you think that this is not a significant, not a major problem. But unbeknownst to you, right? Unbeknownst to you, behind 20,000 is 1 million. Behind 1 million is 50 million. Wow, you might be in trouble, right? Because actually, this is misleading, right? Now you can imagine the situation. See my statement again, right? The possibility of losing more than 20,000 is only 1%. So you, again, automatically you are thinking in your mind that this is not a major problem because only the chance of losing more than 20,000 is only 1%. But again, you didn't realize that behind 20,000, it could be what? Could be 50 million. Because more than 20,000 could be anything, right? Could be 50 million, could be anything. That's why after the crisis or during the crisis, regulators and also experts were proposing the expected shortfall. So expected shortfall doesn't measure only one point, but all points or the average of all points behind the VaR. So the average value behind VaR, not only the VaR point, right? So maybe we could see an example here to make it clearer. So you see, right, there are two events here, two possible things, right? Two possible scenarios. The first one look like this: the probability of 50%, 49, and 1. And here is 50, 49, and then the 1 is 25 and 75. So if we calculate the expected return, so 50% multiplied by 100 but plus 49 multiplied by 80 plus 1 multiplied by 920, and similar to this one, right? So we find out that their expected returns are the same actually, right? Their expected returns, so again, probability multiplied by each expected return or each possible return, right? So the weighted average, right? So we find out that the expected return, their expected returns are actually the same. However, the VaR, so the VaR is also the same, right? You see here, the VaR of 1% is minus 920. So we are saying that the possibility of losing more than 920 million is 1%, and nothing else behind it. So for the scenario A. For scenario B, you see, if we talk about the VaR, it would be the same, right? Because here's the position. Maybe we can draw it. So this is what? Minus 920. Right? So for both cases, the possibility of losing more than 120 million is 1%. However, you see the scenario B, right? Scenario B has something behind it, 1.7 billion. Wow, this is very dangerous, right? They have the 1.7 billion, 1.7 billion, okay? And the possibility of happening for the scenario B, this is 25%, and this is 75%. But if you ask about their VaRs, right, their value at risk of 1%, both would be the same, right? Both for scenario A and scenarios A and B, right? Both will have the VaR of 1% of 920 million. So the possibility of losing more than 920 million is 1%. However, you see the scenario B, behind 920 is 1.7 billion. This is very dangerous, right? And even the possibility of happening is quite big, 75%, right, of the one, right? So 75% of 1%, right? So, what about the expected shortfall? Expected shortfall of A is the same with the VaR because it has nothing behind it. Or even if there's something, I think it's minuscule, right? It's insignificant. But you see the expected shortfall of B. This is scary, right? So 25 of 920 and 75 of minus 1.7 billion. So the expected shortfall for B is 1.5 billion, whereas the VaR is only VaR of 1% is only 920 million. So this could be misleading, right? And this is what actually happened during the 2008 to 2010 crisis. The regulators got myopic, right? Short-sighted. Yeah, you can say short-sighted or even misled, right? They were misled by the VaR measure. It looked, not that risky, but actually was super risky. That's why a lot of financial institutions went down. Another method you could simply adjust the still remember the coefficient on the sigma. So another method is you change the distribution now. So 2.33 is for the VaR of 1%, right? Remember, but if you want to calculate the expected shortfall, you can change it to T distribution. I hope you still remember a T distribution. We call it student T distribution. What distribution is that? It's not normal. It's fat tail distribution. Fat tailed. So the tails are fat, right? That's why we call it fat tail distribution. Okay, here. So according to the normal distribution, for the 98% confidence interval, the coefficient is 2.33. But according to the T distribution, the fat tail distribution, this is 2. Whatever is it? What was it? 2.6, 665. Okay, so if you want to calculate VaR, you can use the Z or normal distribution, like 2.33 for the VaR of 1%. But for the expected shortfall of 1%, you can change the coefficient to the T distribution coefficient, which is 2.665 for a confidence interval of 98 or expected shortfall of 1%. Okay, so this is the another way, right? The lazy way of changing, simply changing the coefficient on the sigma. So you see the example here. Now, where's the story here? Here, standard deviation of the daily percentage changes in the spot exchange rate was 44.3 basis points. So you multiply it, right? This is the sigma, right? 44.3 basis points. So 0.00443 multiplied by, this is the coefficient, but for expected shortfall, you are using the coefficient from the T distribution, the fat tail distribution. Right? So you get this much volatility, and then you multiply the volatility by the exposure. The exposure amount here in this story is this one at 1.2 million somethings. Okay. Yeah, this is the spot rate, and this is the amount of money that you are at stake. 1 million euros at this spot rate. So you divide, right? They're the same in front, you see, the currencies. So you divide, you get this. This is the exposure in US dollar because you are an American company, right? So exposure multiplied by volatility. So you get the expected shortfall. Okay, so simply change the coefficient, right, from the Z distribution to T distribution. Okay, so the last part, now we are going to see the regulatory models. So all the four methods that we just discussed are called the internal models, right? Internal models are allowed, right? Allowed as long as you get approval from your regulator, right? If you're in the United States, you need to, of course, you get approval from the Federal Reserve, right? If you are in central bank in your country, maybe like in Germany, in Indonesia, you have to get the approval by the many institutions, right? OJK, the Bank of Indonesia, and some, including Ministry of Finance sometimes. Right? Okay, so what is the regulatory model allowed? The official model. So what we have seen, the four models are internal models. So internal models are allowed as long as you get the approval. This is a regulatory model, right? The official model. So let's go straight into an example to get it clear. See the situation here. You have a trading portfolio, right? So big problem with market risk could to send you down, right? Because this is for trading, right? For trading purposes. So you hold what? 500 shares of Verizon at 47.25, okay? And then you have what? 20 shares of Goldman Sachs at 206.40. What else? You have 4,200 shares of Lloyd's Banking at 526. Your long position, right? The Verizon, Goldman Sachs, Lloyd's Banking, right? Your long positions. Now you have a short position here. Short position, Deutsche Telekom, right? Deutsche Telekom at 1635 and 50 Goldman Sachs shares. So you see Goldman Sachs appear both, right? You have a long position, the what's that, buying position, and also you have a short position. Short position is like selling, right? Maybe you're doing a short selling, or you have a long put option, or you have a short futures position, right? Or anything. So you could find the difference. Okay, you have a short 50 and you have here 200 long position in Goldman Sachs and 50 in short position. So the net position would be what? 150, right, for Goldman Sachs. So you have 150 net long position in Goldman Sachs because again you have 200 long position and 50 short position. Oh, here, right? So we have 150 long position to Goldman Sachs, right? 200 minus 50. Okay, so see the buckets here. Buckets have been prepared by, again, the BIS, okay? So has been regulated by the BIS. So bucket number according to whether it is like an emerging market or a developed country, right? And then large or small. So large means market cap more than 2 billion, right? Market capitalization more than 2 billion is defined as large. If it's below 2 billion, the market cap is below 2 billion, then it's considered small. Okay, so now we have to make the categorization, right? Categorization, you see, we have what? Verizon. Verizon is telecom company, right? Telco company. Goldman Sachs is financial institution, right? Banking. Here, Lloyd Bankings is another financial institution. And Deutsche Telekom. Deutsche Telekom is telco. So we have these examples, right, to make it easy to imagine. So we have two telco firms and two financial institutions, right? So let's see here. If this is and what's that? Verizon, American company, Goldman Sachs, American company. So obviously, the United States is what? Emerging or developed? Yeah, obviously developed. Right? So telco. So it's about what? About 5 or 6, maybe 6. Bucket 6 here. Bucket 6. Okay, so Verizon and Deutsche Telekom are included in bucket 6, right? So developed market for telco. What about the other two? The other two are Lloyd's Banking Group uh, and Deutsche Telekom. Yeah, Deutsche Telekom is obviously a German company. Lloyd's, I think, most likely British company. So also developed markets for banking. So where is it? Financial here. So bucket number 8. Yeah, correct, right? Bucket 8. So we have bucket 6 and bucket 8. And what is the meaning there? It's very important because bucket 6 will have a risk weight of 35%. So this has been researched and decided by the BIS. Okay, so we don't make it up, right? We don't change the numbers, of course. It's not like beautiful numbers that you choose or something. No, it has been research and part of their decision. And it might change from one Basel Accord to another, right? Maybe Basel the fourth, we'll see another risk weights, other risk weights. But for now, bucket 6 has a risk weight of 35 and bucket 8, 50%. And then we put into the formula, okay? It's very easy. So let's do it. But before we do it, we need the correlation, right? We need the correlation. So risk weights have been decided, right? Bucket 6 and bucket 8. But now we need to see the correlations between the assets, right? So let's see the first one. What is it then? Verizon and Deutsche Telekom, right? Verizon and Deutsche Telekom here. This is long position. You hold, right? You buy, right? So long position here. But the Deutsche Telekom is short position. Okay, so have to be careful now here. For the bucket number 6, the Verizon, we have a long position in Verizon, but a short position in Deutsche Telekom. So different sign, right? So the correlation is 15%. Okay. So what about the other two? What's that? Lloyd Banking, right? Lloyd's Banking and Goldman Sachs and Lloyd's Banking. So Goldman Sachs, we have my long position is 200, the short is 50. So net long position, right? 150 is still long, right? Net long position 150. And what's that? The Lloyd Banking is also long position, right? So both are long positions. What is the meaning here? For bucket 8, the correlation is having the same sign. Okay, so for the bucket 6 that we have, the positions are different, right? Opposite positions, but for bucket 8, right, between the Goldman Sachs and Lloyd's Banking, they have the same position, right? The long position. Okay, then we put into calculation, right? Put into calculation. This looks a lot of numbers, but actually it's very easy, right? What is it? Risk weight squared. Risk weight squared multiplied by, what is it? 500, what is it? Verizon, I think. Yeah, 500 is Verizon, right? 500 shares multiplied by the stock per share. So this is the market cap, right? Market value that we are having. Let me repeat from clean slate. Okay, so 0.35 is the risk weight. Disappears. Yeah. Right, 35%. This is what? 500 and 47, right, for Verizon. Yeah. Plus 35, this is for who? For Deutsche Telekom, bucket 6, right? The risk weight is 35. Multiplied by, you see the Deutsche Telekom, yep, here. Multiplied by what? 1635. Squared, right? Squared. Yeah. Plus, okay, this looks like a portfolio model of Markovitz, right? So 2 multiplied by, no, this is a correlation. Correlation for 6, right? This is bucket 6, K6. Different sign, right? Between the, what's that, Verizon and Deutsche Telekom. Verizon has a long position. Deutsche Telekom is a short position. So different sign. So 2 times 15% multiplied by the risk weight of Verizon multiplied by the market value of Verizon multiplied by risk weight of Deutsche Telekom multiplied by the market value of Deutsche Telekom. And then we get the variance, right? To get the standard deviation, we square root, right? You find the square root of it, right? To the power of half, or the square root of it. So we get, okay, now 10,738 for K6, right? So what about K8, right? K8, the bucket number 8, between what? Goldman Sachs. In this simple example, we only have Goldman Sachs and who's that again? Lloyd's, right? Lloyd's. So what is the risk weight for bucket 8? 50%, the risk weight. So 50% square multiplied by, this is who? Goldman Sachs. Remember Goldman Sachs? They have a long position of what? 200. But you have a short position of 50. So it's 150, right? In a net long position. So 150 multiplied by the price, right? 240. Let's check again. Where is it? Goldman Sachs. 200. Yeah, here. 240, right? Right? Plus 0.5. This is again the risk weight for bucket 8. 0.5 here. Square multiplied by, what is it again now? Lloyd's Banking. You have 4,200 shares at 526. So multiplied by 4,200 shares multiplied by 526 squared plus now 2 times the correlation, right? The correlation for bucket 8. Now both have long positions, right? The Goldman Sachs and Lloyd's Banking. So it's this one, right? Same sign, same position. So plus 2 times 35% times, this is the risk weight of Goldman Sachs multiplied by the market value of Goldman Sachs multiplied by the risk weight of Lloyd's Banking multiplied by the market value of Lloyd's Banking. And then you get the variance. And of course, you have to find the square root of it to get the standard deviation, right? So you get 21,000 something for bucket 8. So you have bucket 6, you have bucket 8. You see, right? In real life, this would be a tiring process, right? Even in our example, in K6 and K8, we only have like 2 and 2, right? 2 instruments and 2 products and 2 products. Can you imagine if we have like 100 in K6, 80 in K8, then we need computers, right? We need the we need the software on your computer or laptop to calculate. You can do it manually like this, but this is an example, right? But with Excel, at least you can do it. Okay, so you find the total here, right? Similar to the Markovitz method. So you have standard deviation from K6. You have standard deviation from K8. Then we combine them, right? Here, what is it? This is the standard deviation of K6. This one, right? Here. Squared plus this is the standard deviation from K8 squared plus 2. Now we need the correlation between what? Between buckets. So we have bucket 6 and bucket 8. Where is it? Here. Correlation between, 20%, right? So times plus 2 multiplied by 20%, the correlation between the two buckets, right? Now multiplied by, so 1 by 1, right? Risk weight of Goldman Sachs, what is it again? Verizon, right? Risk weight of Verizon multiplied by the market value of Verizon plus risk weight of Deutsche Telekom multiplied by the market value of Deutsche Telekom, and then multiplied by, so you see here, plus, right? So you have to be careful here. You have to solve this one first. Right? Because there's plus there. So you finish the Verizon and Deutsche Telekom, and then the result will be multiplied with this one, right? This is what risk weight for Goldman Sachs multiplied by the market value of Goldman Sachs plus risk weight for Lloyd's Banking multiplied by the market value of Lloyd's Banking. So again, you have to finish this in bracket. Right? And then the whole result should be, you should find the, what's that, square root of it, right? You find the square root of the result, and you get 27,296. So this is the very important figure. This is a capital charge that's sourced from market risk. So in our next discussion on capital adequacy, you'll see that capital adequacy traditionally is contributed only by credit risk. You see, a capital adequacy ratio means your capital divided by your risk-weighted assets, right? Capital divided by risk-weighted assets. So traditionally, this is only sourced from credit risk. However, in the revised version of Basel I, they added market risk. So this is it, right? Why we take effort to calculate this amount, this number? Because this is the additional capital charge to your car, sourced from market risk. Okay, so you see in our next discussion, there's another source named liquidity risk. Right, so we have credit risk, we have market risk, we have we have operational risk, right? The third one. So credit risk, this is market risk, operational risk, and then for the Basel III, I think this will be effective in 2022. We have to include liquidity risk as well. Liquidity risk charge, additional charge to the capital adequacy calculation that is sourced from liquidity risk. That would be the fourth one. But here we are looking at market risk, right? So 27,000 is the additional capital charge that has to be added to the capital adequacy requirement. That's why we are taking the effort to calculate this, right? Otherwise, why should we? Okay, so what about the internal models? Again, you should use the here, this one, right? DEAR means what? Value at risk for 1 day multiplied by the square root of 10. It means that for 10 days, and you have to add what's that? The factor of 3. Factor of 3. So if you want to use the JPM risk matrix, then you have to do it. So your VaR or DEAR, daily VaR, right? Of course 1%, right? Then you have to calculate for 10 days, right? Multiplied by the square root of 10, and then you have to multiply by 3. Right? And then the new regulation says that the capital, if you want to use this method to estimate your capital charge, right? Again, the additional capital charge that is sourced for market risk, you have to plus the stress VaR. So stress VaR means this is what value at risk when the situation is stressed out. Stressed out situation means what? High interest rate, high inflation, bad economic growth, such as maybe today, right? This is a very bad economic situation, right? Stress situation. So you can estimate what would your VaR be in a stressed situation, right? Multiplied by square root of 10, multiplied by 3. So this would be the capital charge. If you want to use the internal model, but if you want to use external model, then yeah, it would be this method, right? We call this one what? Partial risk factor. Partial risk factor method. So this is a method, official method to estimate your additional capital charge to your capital adequacy ratio sourced from market risk, right? But if you want to use the internal model, then you use this one, right? The what's that? Value at risk or JPM risk matrix. But you have to plus, right, the new regulation, right? Okay, I think we have discussed quite extensively about market risk today, and of course, in the next discussion, we'll continue with capital adequacy. But remember that from time to time, right, from one generation to another, we will see changes in regulations, right? So all numbers, all risk weights, all formulas and equations will change, right, from time to time, and we have to always check, right? Okay, so thank you very much for following the discussion today, and see you next time.